With that, I will introduce the first speaker today. This is David Trimas from University of Michigan, and the title of his talk will be Evaluation of Recoil Rates in CEVNS-based detector for reactor anti-neutrino monitoring. David, the floor is yours.
Thanks, Professor Jovanovic. And thanks everyone for the break. It was a perfect amount of time to get myself some more iced coffee, which I really needed. Without further ado, let's get into this. So I'm actually in a perfect position right now in this talk because I think a lot of people have talked about the different antineutrino detection methods. So you're familiar with it, and also their importance and relevance to the NNSA mission. But I'm gonna sort of reiterate that a little bit. So it's really important to detect plutonium production and plutonium removal possibly in a reactor for nuclear nonproliferation purposes, because there's the possibility of creating a nuclear weapon with that material. And reactor antineutrinos are a great signature to look at nuclear fissions to determine the plutonium content in nuclear fuel. I know, for example, Felicia and several others already said that it can't be shielded. You can't easily spoof a neutrino signal because you need fissionable material to do it. You actually need actively fissioning material to do it, in fact, and it relays information about the isotopic composition of that fuel. So there's already been a few methods discussed, namely coherent scattering of neutrinos and inverse beta decay for detecting antineutrinos, but I'm focusing on coherent electron neutrino scattering, also abbreviated as CEVNS, and I'll be talking about that a little bit. So it's relatively new compared to inverse beta decay, but it has its advantages. So it has no energy threshold, like the 1.8 MeV that we see for inverse beta decay, and it also has a higher cross section. So first, I'll sort of talk just briefly about what CEVNS is. It's a coherent interaction, so kinetic energy is conserved during it, and it's not only limited to reactor monitoring. That's what I'm interested in, reactor and spent fuel monitoring, but there's applications for it for beyond standard physics models, and even astrophysics and dark matter. They use several of the same technologies that we use to detect dark matter candidates. It's very similar technology. So there is like a widespread community for CEVNS right now. The first point that I said was that CEVNS has a higher cross section than IBD. And you can especially actually see this in the energy regime of fission neutrinos. So in the regime of fission neutrinos, CEVNS cross-section is several orders of magnitude higher or a few orders of magnitude higher. It depends on what isotope you're talking about for the actual target material of the detector, because there's that neutron squared dependence of the cross-section. So the amount of neutrons in your target nuclei, how many there are, changes what that cross-section is. It's also equal in cross-section for both neutrino and antineutrino, but since most fission signatures are going to be antineutrinos, we're going to focus on antineutrinos today. However, though, CEVNS is much younger than inverse beta decay. For example, like we had people from the coherent collaboration here earlier today. First event was not detected until 2017, and then again this year in 2020 in liquid argon. So it's a pretty young field, but there's a lot of opportunities to explore. And just like any other field, we have to stay up to date with what's going on. So this is something very important to look at for nuclear nonproliferation, since it's a developing technology, a developing theory in physics. I mean, the physics has been laid down for a while, but this is something that we can look at right now. So what I'm going to specifically be focusing on today is dual phase noble element time projection chambers for CEVNS detection. So hold on, let me move the view of the people so that I can actually look at all my slides. Sorry about that. So for these detectors, I'll kind of explain a little bit what happens inside of the detector. So you have an antineutrino that comes in, that's shown in red here. And then it scatters off of a nucleus which is in a liquid phase here in this example. And that imparts some energy onto that nucleus. And then it creates either prompt scintillation light and also ionizations or just ionizations. It depends on how much energy it deposits. For reactor antineutrinos, you're really only going to see those ionizations. The S1, which it's called here, this scintillation light typically only happens for ionizations, or sorry, recoil energies that are above that which you see from reactor antineutrinos. So we're just going to follow this ionization up to the gas phase. There's a electric field that drifts this up. And once it gets here, it's able to actually produce more scintillation in the gas phase, which is above this liquid phase, via electroluminescence. Sorry, I meant to say via, and I almost said veto, but via electroluminescence. This is detected with either PMTs or silicon photomultipliers, and this signal is proportional to the amount of ionizations created. We use typically noble elements for these type of detectors because they have a low electron recombination probability, which is important if we're drifting electrons through this liquid phase. And also they have a sufficient scintillation yield in the gas region, which is what the S2 scintillation light is what we really care about here for reactor monitoring. And also they have low chemical reactivity, and they're relatively inexpensive to purchase a large amount of argon or xenon, for example. Moving on here, the next thing I want to talk about is how fissile isotopes, each one of them has a distinct neutrino spectra. And this is important because once you actually detect a recoil spectrum, you want to know where that recoil spectrum came from. And you can actually tell what sort of source it was based off of what that recoil spectrum looks like. So here I plotted, the 4 most important isotopes in a reactor for antineutrino signals. And you can see, especially at higher energies, that they have a distinct spectrum. And also even at the peak near 1 MeV-ish, they have different amounts of neutrinos emitted per fission. So this is very important for being able to figure out what's actually in the reactor at a certain time. So this change in the amount of isotopes that are in the reactor at a certain time. So I'm saying, throughout time, you're going to get a plutonium buildup, for example, in the reactor. This actually leads to a change in the neutrino spectrum, which then in turn leads to a change in the detected signal. So this is important because first off, you can just look at the reactor and monitor what types of isotopes are inside of it. And also you can look at it and see if there's any anomalies. Is there less plutonium than you expected? That might indicate that there was a plutonium diversion, for example. You can especially see these, I want to reiterate this, at the higher energies of neutrinos. So this is a little bit important once you get into deeper analysis, because that means you want to look at those, higher energy events, because that's where you're really going to see the difference. So now I'm going to kind of get more into, this is going to build up on itself until I show you some calculations I did for plutonium removal. But we're going to start with talking about ionization yield in the detector medium itself. So it's a probabilistic process. So you have a recoil of a given energy, and it will produce some amount of ionizations, but it's not going to always produce the same amount of ionizations for the same recoil energy. It's actually approximated well by a Poisson distribution. So you may see, for example, if the mean number of ionizations produced by a certain recoil energy is 3 electrons, you might actually see, 3, 2, 1, 4, 5. You could see any of these with a certain probability. You could even see 0. It could produce no ionizations. So this is something that you take into account when you're actually predicting the response of your detector to reactor antineutrinos. And then next, you actually get to the detected signal, which is those S2 photons. So first off, after you produce those ionizations, they have to make it through that liquid phase to the gas phase. So there's some sort of extraction efficiency that you can assume for the detector. In these examples, I'm being pretty conservative, and I'm saying the extraction efficiency is 50%, and that's sort of a binomial distribution there. So for example, if you had 10, I'm doing 10 Bernoulli trials at 50% probability of making it out of the liquid phase. So that's this bottom plot here, bottom left. And then after that, once they make it to the gas phase, they can produce any amount of photons. And I modeled that with a Gaussian distribution. And then I also incorporated the light detector efficiency to actually show an example of what a detection spectrum would look like in units of detected photons. So you can kind of see the quantization of this plot here, because you have the single electron peak. So this is when you have one ionization peak and it produces a certain amount of photons that you detect. And then you go down, you have 2 ionizations. And then after that, it's really hard because it's a continuum where you just see a lot of those different peaks sort of meshing together to just form one little continuum here in the higher amounts of photons detected. But this gives you a general idea of what you sort of are going to look at when you see a detected spectrum. But this is without background, but we're getting there soon. So the reactor fuel cycle is one thing we can observe with CEVNS. This is the first thing I'd want to look at. Hold on a second, I gotta Sorry, almost had to sneeze. Or sorry about that. So on the left here, I show a representative ionization spectrum for reactor antineutrinos. And then this is for a 3 gigawatt thermal, 4% enriched PWR detector. This is 25 meters from the reactor itself. And then more interestingly on the right, I show the amount above background of the detected signal for a 7,200 kilogram day measurement, which means I take the active mass of the detector and I multiply it by the number of days for the measurement. And that gives me the size, sort of like how big that measurement is, because it depends both on the mass of the detector and the time that you are recording. And I looked at different times in the fuel cycle to see how much above the background I was. I got about 3.5 sigma at the beginning of the fuel cycle. And then that continues to decrease as the fuel cycle ages. And this is because plutonium actually doesn't emit as many neutrons as uranium. And also it's a little bit softer as well, which makes it harder to detect above background. This is for a signal to background ratio of 0.1. So I just have the background being 10 times that of the detected spectrum in this example. I also just wanted to compare this sort of to IBD. IBD has demonstrated 5.5 sigma for the same measurement time, so 7,200 kilogram days. And so it's you know, like I said, it's a developing field, so I don't think you should just rule it out right away just because it's lower above background confidence. This is still, you know, good, and I still think that I really support this, especially because it's a 50 kilogram detector as opposed to in the case of Mini Chandler where you have, you know, tons of detector material. So that's like, I think the big attractiveness of it is you can have a compact detector here. So now I'm going to go on to a possible scenario where I sort of divert some plutonium from the reactor. So I take out some of this irradiated fuel after a year, where after a year, there's a significant amount of plutonium-239 in the reactor, but there is not so much plutonium-241 that it doesn't rule it out for use as a nuclear weapon, for example. And then after this, I put fresh fuel in to replace this extracted fuel to maintain reactor power. I then calculate the time to detection with 1, 2, and 3 sigma confidence. And again, I assume just this signal background ratio of 0.1. And I just to mention, after 1 year, this irradiated fuel contains about 4 kilograms per ton of plutonium-239 for a 4% enriched PWR. So actually for this 3 gigawatt thermal PWR, which I'm showing now, the results for this is corresponds to a full core swap being about 120 kilograms of plutonium-239. So what I'm actually showing here is the amount of plutonium that I remove, and then the amount of time it takes to detect it with a certain confidence. So the black line here is 1 sigma confidence, the blue line's 2 sigma confidence, and the red line's 3 sigma confidence. And like the big things I wanted to point out here, first off, this is 20 meters away. This is, I mean, you can probably get a little bit closer, but for a large reactor, I don't think 20 meters, you're going to get much closer than that. So I think this is pretty, you know, good place to put the detector, a near field detector. Within 3 months, you're able to detect 40 kilograms of plutonium removal with 1 sigma confidence. And then just another thing to look at is a full core swap. You can detect with 1 sigma confidence in 10 days and 3 sigma confidence in about 2 months. So there is the possibility of detecting plutonium removals using CEVNS. In conclusion, CEVNS has the capability of providing a compact way of reliably monitoring reactors. And you can see below that 1.8 MeV IBD threshold, which also opens the possibility for spent fuel monitoring, which has a softer neutrino spectrum than just reactor antineutrinos. That's important, obviously, because we want to also, you know, have some sort of safeguards on our spent fuel. And future work is currently underway at Lawrence Livermore to develop these detectors for the specific purpose of both reactor monitoring and spent fuel monitoring. I just want to say one more thing. I think I might be over time, but I'm just going to try and go through this quickly. There still does need to be ionization yields for liquid argon, which is what I was talking about, at the energies of interest for reactor monitoring, which is 300 EV to 5 keV nuclear recoil. And also background needs to be studied at low energy so that we can possibly in the future discriminate or suppress it. I'm involved with both of these at Lawrence Livermore National Labs. And thank you for your time. That's all I have today.
Thank you, David. And I think this is how I applaud. This paper is open, or this talk is open for questions. So please either raise your hand or ask a question on the group chat. And I'll see if so we don't have any questions on the group chat. Okay, so here's the first one. And the question is from Ted Boyer. And the question is, do you think that argon-39 could contribute to the low energy background?
Yeah, I do, because it undergoes a different interaction. So you can put it into an excited state and then it decays in a certain way. I think that actually, so there is someone at Lawrence Livermore who's studying that actually. So like I'll get back to you once we know more about it, you know, but I do think that it contributes to low energy background. So yeah.
Okay, so a question I'll ask is, David, can you talk a little bit to the, technological challenges here with detecting simulation, from these novel element?
Yeah.
And what are the considerations there? What are the main challenges?
So the actual detection it's quite a challenge. So like I said, like what you detect is that S2 scintillation light, which is emitted in the UV regime around 120 nanometers. So the problem is that's not the most sensitive region for PMTs, for example, or typical silicon photomultipliers. So you actually have to look into using like specifically made UV photomultipliers for this specific application. Hamamatsu has released recently some VUV silicon photomultipliers that we're looking into using because they may have about a 10% improvement in detection efficiency. So that's like one thing that's been sort of like improved very recently as far as detection is concerned. I don't know if that's exactly what you were asking, but like that's like one thing I can say about that.
Thank you. No, that's a good background, and
Okay.
I think that those are important considerations technologically. There's a comment from Ted Boyer as in response to your earlier
Okay.
earlier question, and the comment is that there are some efforts to mine clean argon, and
Yeah.
so
Underground argon. Yeah. Dr. Jinkazu, who's one of the people I work with, he's at Lawrence Livermore. He's been working actually for quite some time at getting underground argon. So that's like another thing that hopefully in the future will pan out sort of. I don't know if that's still ongoing. I like don't know a lot of details about the underground argon. I haven't talked to him a lot about it yet, but that's something that I think will be beneficial in the future to suppressing background in argon.
And just the last question from Professor Vihi, how is the S1 signal used?
Oh, okay. So the S1 signal, it's a little bit tricky for reactor monitoring because you need enough recoil energy to actually see it. If you don't have enough, I don't have like a specific answer for like how much energy you need to actually see S1 scintillation light, but if there's not enough, it's not going to occur. So the problem is for reactor antineutrinos, I know for sure like the vast majority of the time you don't see any S1 scintillation light. For higher energy neutrinos, you could get enough recoil energy to see it. And the good thing about that is you can use it as sort of a timing tag to tell how long that electron took to drift up, and then you can actually tell depth-wise where it occurred in the TPC. So that's where you would use it, and it's also just an additional signal, and it's always better to have more information. But unfortunately for reactor antineutrinos, the energy is just not going to be high enough to produce S1 scintillation light.
Okay, thank you, David.